Okay, welcome to this recorded presentation of a new LB&L report titled Maximizing Megawatt Hours, a Statistical Analysis of the Performance of Utility-Scale Photovoltaic Projects in the United States. My name is Mark Bollinger. I'm with Lawrence Berkeley National Laboratory, and I co-authored this study with my Berkeley Lab colleague Joachim Seal, as well as Manfei Wu from the Goldman School of Public Policy at UC Berkeley. This work was funded by the U.S. Department of Energy's Sunshot Initiative, and we appreciate their support. So let me start off by providing a little bit of context for this report. Last September, we released the latest edition of Berkeley Lab's annual Utility Scale Solar Report, which found, among other things, that net AC capacity factors among a large sample of utility-scale PV projects in the U.S. varied by more than a factor of 2, ranging from about 15% to roughly 35%, and that's in AC terms. And by that I simply mean that we use the AC rather than DC capacity of each project in the denominator of the capacity factor equation. So the purpose of this report is simply to investigate, using multivariate regression techniques, what's driving this significant variation in performance. For example, might this variation be be attributable to certain projects underperforming, or is it instead largely explained by other variables that can influence capacity factors like the strength of the solar resource or the use of tracking? Answering these questions and understanding how these existing projects have performed, as well as what drives variation in performance across projects, is important because the profitability of the utility scale sector ultimately depends in large part on how well these projects perform over time. And how profitable the sector is will in turn directly affect its ability to attract the large amounts of investment capital needed to fund ongoing deployment at the pace envisioned by state, regional, national, or even global targets. Moreover, although federal tax credits have recently been extended for a few more years, the importance of project performance will only increase in the future as the federal investment tax credit is gradually phased down from its current 30% level to 10%, thereby leaving a greater proportion of each project's overall after-tax profit dependent on revenue that's tied to the number of megawatt hours generated. So bottom line, it's important to understand how these utility-scale PV projects are performing and what's driving variations in performance across projects, which is why we undertook this analysis. Now, as I've already intimated, in order to compare performance across projects, we focused on each project's net AC capacity factor in the year 2014. Another option that we considered, but ultimately rejected, was to look at cumulative capacity factors, given that some of the projects in our sample have been operating since as far back as 2007. But we ultimately decided to focus on just a single year, 2014, for 3 reasons. First, the bulk of our sample is very young. As you can see in the table on the bottom right of this slide, more than a third of all projects and more than half of all capacity in our sample was built in 2013, which means that 2014 was really the first full year during which we could calculate a capacity factor for much of our sample. And I should probably just pause here to quickly note that for variable generation resources like solar and wind power, it's important to measure capacity factor only in full year increments so that seasonal influences don't come into play. Now, given that the strength of the solar resource can vary by 10% or more from year to year, it seemed inappropriate to compare capacity factors in just 2014 for those projects that came online in 2013 to capacity factors over a longer period from maybe 2008 through 2014, which is what we would need to be doing if we were looking at cumulative capacity factors. Second, data availability also favored a focus on 2014, given that we were able to obtain site-specific installation estimates for 2014, but not for earlier years, from Vaisala, which is a respected wind and solar resource consultancy. Finally, focusing on the most recent individual year, which in this case was 2014, allowed us to isolate the potential impact of time, which could help to shed light on empirical module degradation rates. So for these three reasons, the dependent or left-hand variable in our regression models is net AC capacity factor in the year 2014. Now turning to the other side of the equation, this slide lists possible independent or right-hand variables that could influence capacity factor. Obviously, the strength of the solar resource plays a significant role here, and as I mentioned, we were fortunate to obtain site-specific estimates of average annual global horizontal irradiance, or GHI, from Vaisala for each of the projects in our sample. The use of tracking devices will also boost capacity factors by increasing the irradiance that falls on the plane of the array. The inverter loading ratio, or ILR, simply measures the capacity of the DC array relative to the AC inverter rating, and a higher ILR can boost capacity factor by causing the inverter to operate closer to or at full capacity for more of the day, and in particular during the morning and evening shoulder periods. Project vintage can be a little bit tricky because it's tempting to think of efficiency gains in PV modules as potentially contributing to higher capacity factors among more recent projects. But in reality, as module efficiency improves, developers simply either use fewer modules to reach a desired amount of capacity, or else they use the same number of modules to boost the amount of capacity installed at a given site. And either of these approaches will result primarily in cost savings rather than capacity factor improvements. That said, vintage is nevertheless still important for our purposes here, given that PV module performance tends to degrade over time, which means that all else equal, we would expect to see older projects have lower capacity factors than newer projects. The orientation of the array is obviously important, particularly so for fixed tilt projects. Unfortunately, we lack good data on tilt and azimuth, although for projects of this size, which can cost upwards of tens or even hundreds of millions of dollars to build, I think we can safely assume that orientation will likely be optimized across projects to maximize generation. And if that's true, then it means that we can probably ignore this variable, as it will not really add any explanatory value to our model. Finally, temperature is another driver in two ways. First, all modules perform better at lower temperatures, and second, it's also the case that some modules perform better than others at higher temperatures. Unfortunately, though, we lack good data on the power temperature coefficient, as it's called, as well as cell operating temperatures. And as a result of these data limitations, we exclude both temperature and orientation from our models, and instead focus only on the first four variables in this list. Okay, here we see some descriptive statistics for the sample, along with a histogram showing the distribution of capacity factors among both fixed tilt and tracking projects, as well as in aggregate. And you can see that capacity factors vary by more than a factor of 2, with a bit of a bimodal distribution that reflects the difference between fixed tilt and tracking projects, each of which makes up roughly half of our sample. Though not shown here, I think it's somewhat interesting that fixed tilt projects have a slightly higher average inverter loading ratio than do tracking projects, which makes sense given that a higher loading ratio is somewhat redundant with tracking, in that both a higher loading ratio and tracking tend to boost production during the morning and evening shoulder periods. This next slide continues with the descriptive statistics, in this case broken out by state. The top 5 states in terms of capacity factor account for the vast majority of both capacity and projects in the sample, with California alone making up 49% of the capacity and 32% of the projects. In the final column over on the right, you can see that tracking tends to be more prevalent in states with higher insolation, which is intuitive in the sense that you get more bang for your buck tracking a stronger rather than a weaker resource. Here's another way of looking at the sample, broken out by 3 of our 4 independent variables, with only project vintage or COD year not included in the graph. There's obviously a fairly strong positive relationship between capacity factor and ILR tracking in GHI, particularly among the mean values depicted by the blue columns. The individual projects, which are shown by the circle markers, do of course show a bit more variability, which is why we need to use regression techniques to take a deeper look. Now, in addition to our 4 primary independent variables that I've already mentioned, we also included 3 interactive terms to try to capture the nuances in how GHI tracking and ILR influence capacity factor in relation to one another. Specifically, we crossed tracking with GHI on the notion that tracking should provide more of a capacity factor boost at sites with a stronger solar resource. We also crossed GHI with the inverter loading ratio for much the same reason, namely we would expect higher loading ratios to provide more of a performance boost at sites with greater insolation. And finally, we crossed tracking with the inverter loading ratio, in this case because we would expect the marginal benefit of tracking to diminish at higher loading ratios, since, as described earlier, the two are somewhat redundant. So overall, we ended up with 7 independent variables, 4 that are non-interactive, and then these 3 here that are interactive. And here we see all 7 of them in this table, which shows how we went about sequentially trying various model configurations as we progress towards our preferred specification in Model 5. Just a few things to quickly note here before talking about results. First, we transformed the inverter loading ratio variable 2 steps down the ladder of powers by taking its natural log. And we did this because the ILR data and residuals seem to warrant this transformation, and it also makes intuitive sense given that we'd expect a diminishing marginal effect as ILR increases, given the greater potential for maxing out the inverter resulting in power clipping. We also centered our independent variables even though we had not detected any heteroskedasticity problems. So the continuous variables are centered around their means, while the COD year variable is based in the year 2007. And of course, the tracking dummy variable is not centered. It's either 1 for tracking projects or 0 for fixed tilt projects. This centering process eases interpretation somewhat, as it means that we can interpret the constant term to be the predicted capacity factor when all independent variables are at their center points. And then finally, just as a bit of a no regrets best practice strategy, we used robust regression techniques, so the standard errors shown below each coefficient are indeed robust standard errors. So you can see in models 1 through 3, and I guess particularly in model 3, that just 3 independent variables explain 92% of the variation in 2014 net AC capacity factor, with all 3 variables and constant terms highly significant in all cases. Adding COD year, which is also significant in Model 4, improves the results a bit further. And then finally in Model 5, which again is our preferred specification, we added the 3 interactive terms as well. Okay, this graph shows the fitted versus actual 2014 net AC capacity factors resulting from Model 5, along with a best fit line. As you can see, the fit is highly linear and very tight, with an R-squared of 0.938 and a root mean squared error of just 1.3%. As you saw on the previous slide, all variables in constant terms are significant, with the lone exception of the interactive term that crosses tracking with ILR. Now, in addition to visually inspecting the residuals, we also ran a number of statistical tests to make sure that our data and model specification do indeed conform to the underlying assumptions of ordinary least squares regression. Those tests are described in the text below the graph, and suffice it to say that I think we're okay on all fronts here. All right, so the next 5 slides walk through the interpretation of Model 5. So here we see a graph that shows the influence of the COD year variable on both fixed tilt and tracking projects, assuming average GHI and ILR levels. Again, because we centered the independent variables, the constant term tells us that a fixed tilt project built in 2007 with average GHI and average ILR is predicted to have an AC capacity factor of just over 22%. Single axis tracking adds just over 4 percentage points, 4.05%, while each successive COD year adds 0.23%. Said another way, Model 5 predicts that older projects have lower 2014 capacity factors to the tune of 0.23% per year on average. Now, one possible interpretation here is that this coefficient is detecting module degradation rates, though it's worth pointing out that 0.23% is at the low end of the range of degradation rates that one often hears, where the typical range from the literature is more like 0.25% up to as high as 1%. Given our natural interest in newer rather than older projects, as well as the need to fix the COD year in order to more easily interpret the influence of other variables, the rest of the Model 5 interpretation that I'll run through focuses on projects that achieved commercial operations in 2013. So here we see the influence of GHI on a 2013 project with an average ILR. As you can see, the benefit of tracking increases with higher insolation, which makes intuitive sense and is also consistent with the greater prevalence of tracking at higher GHI sites, as we saw in earlier slides. And here we see the influence of ILR on a 2013 project with an average GHI. As mentioned earlier, a rising ILR provides a slightly diminishing marginal boost to capacity factor as it increases, and this is likely due to greater amounts of power clipping occurring at very high loading ratios. Finally, the only remaining variable left to explore is the interactive term that crosses GHI with ILR. Now this one's a bit more difficult to present given that it involves an extra dimension. So here we show the results in tabular rather than graphical form, and I will attempt to walk you through this. So first let's focus on the two orange shaded rows labeled A. These show the difference in capacity factor between one project with an ILR of 1.45 and another with an ILR of 1.10 at different levels of GHI for both a fixed tilt project, which is shown in the upper part of the table, and a tracking project, which is shown in the middle part of the table. What you see in these orange shaded rows is that the benefit of a higher ILR increases at higher GHI levels, which makes intuitive sense. Moreover, for any given GHI, the benefit of a higher ILR is slightly greater for fixed tilt than for tracking projects, which is also intuitive given the potential redundancies between these two that I've already described. Okay, next let's focus on the two blue shaded columns labeled B. These show the difference in capacity factor between one project with an average GHI of 5.5 kilowatt hours per meter square per day and another with an average GHI of 4.0 kilowatt hours per meter square per day at different ILRs, again for both a fixed tilt and a tracking project. And what you see in these blue shaded columns is that the benefit of a higher GHI increases with higher ILRs. Moreover, for any given ILR, the benefit of a higher GHI is greater for tracking than for fixed tilt projects. And again, both of these findings are also intuitive. Finally, the bottom third of the table simply shows the benefit of tracking at each GHI ILR combination. And what you see here is that for a given ILR, the benefit of tracking increases with GHI, while conversely, for a given GHI, the benefit of tracking actually decreases slightly as ILR increases. And these findings affirm what we saw earlier on previous slides. So hopefully that wasn't too confusing. Finally, this graph is an attempt to summarize the Model 5 interpretation in waterfall format. So from left to right, it progresses from a 2007 fixed tilt project with average GHI and ILR. This is on the far left at 22.02%. From there, it moves on to a 2013 fixed tilt project with a higher GHI and ILR. That's shown in the middle. And then finally, it continues to move on to a 2013 tracking project with the same GHI, same higher GHI and ILR, and that's on the far right at a capacity factor of 35.68%. To wrap this up, the rapid deployment of utility-scale PV projects across the U.S. over the last few years has resulted in a diverse fleet of projects with capacity factors that varied by more than a factor of 2 in 2014. The regression models that I presented here find that just 3 independent variables, namely GHI, tracking, and ILR, can explain 92% of this variation, with GHI alone able to explain more than 70%. Adding COD year or vintage as a 4th independent variable, along with the 3 interactive terms, improves the model further and reveals some interesting relationships between these independent variables. For example, we found that the performance benefit of tracking increases with a higher GHI, but diminishes with a higher loading ratio. Again, we were unable to include any temperature variables due to inadequate data, but such variables would presumably improve the model even further. Now, taken together, the empirical data and statistical modeling results presented here can provide a useful indication of the capacity factor that solar project developers and investors can expect from various project configurations in different regions across the country. Moreover, the tight relationships between actual and fitted capacity factors from this relatively simple model should really instill confidence among investors that the projects, in this sample at least, have largely performed as expected to date. So with that, let me leave you with several ways to hopefully find answers to any questions that you might still have. First of all, you can read the full report, which is freely available at the link shown up top. You can also replay this video as many times as you'd like at the YouTube link shown. Alternatively, and probably more effectively, you can email me or my colleague Joachim Seal at the email addresses shown. And then finally, if you're interested in this type of analysis more broadly and would like to peruse our other renewable energy publications to see what's available, please take a look at the link provided towards the bottom of the slide. Again, we thank the Department of Energy's Sunshot Initiative for sponsoring this work, and we hope that you found this video to be enlightening. Thanks for tuning in.